If you're like many people, you might be staring down midterms and finals. They're coming up and you might be getting stressed. And so to help out, Khan Academy has offered the opportunity for people to ask questions on Facebook and in Twitter. And here's one that came in recently. This was from Konain Ali. I might be butchering that name, Konain. If so, I apologize. But this is a great question. Konain asks, what is an isolated system in physics contexts? And how are the equations involving kinetic energy derived for an isolated system? I like this question because isolated systems are a crucial aspect of understanding energy conservation and one that I think a lot of people have trouble with understanding. So let's talk about this. So an isolated system in physics context is an object or a collection of objects whose energies we're going to keep track of. And that might sound abstract, so let's make this a little more concrete. So imagine, if you will, say there's a book. You probably don't have to imagine this. There's probably books laying all over if you're studying for midterms and finals. So say there's a book lying around. You probably got plenty of these. You probably got way too many books laying around right now. Books sitting around, that's an object. We could say that is our system. Or, you're also there. You're studying hard. You're also an object. We can make you the system, or you and the book the system. There's also air in the room. I'm just going to draw all the air right here. But the air in your room hopefully is not all in the corner. You're dead right now because you can't breathe. So this is just a way to highlight that we can think about the air in the room as a separate element within our energy system. And what does a system mean? It is an object or a collection of objects whose energies we're going to keep track of. So what energies of these objects do we want to keep track of? We can keep track of all of them. It's often a good idea to just put as many things in your system as you possibly can. So we can call this our system. Our system could be composed of the book and the person and the air in the room. Why do we do this? Why do we bother calling it this? Because it's very important to keep track of what energy enters and exits your system. Energy can get transformed and it can get transferred. So for instance, we as a person over here, we can do work on the book, and doing work is just another word for transferring energy. So in other words, I can transform some of my chemical energy and transfer that into kinetic energy of the book. So some of that chemical energy stored up from what I ate in my muscles can get transferred into the book, and that takes the form of kinetic energy. The book starts moving. So we can transfer energy in the book, and once the book starts sliding, it might heat up the table, might heat up the air. So some of that thermal energy might stay in the book, some of it stays in the table, but some of it might leak out into the air over here. So that'd be another transfer of energy, thermal energy into the air. And now that the air is warmer, slightly warmer, it's probably not going to be that much warmer unless you're really pushing this book back and forth a lot. But now that the air gets a little thermal energy, the air around you is a little hotter, so it might transfer some energy into you, or vice versa. If you're hotter than the room, which is probably likely unless you got a pretty hot room, you could transfer some thermal energy back into the air. What I'm trying to say is that energy can get transferred all over the place, and defining our system gives us a way to define what's in our system and what's outside of our system. Because if all the energy in our system stays within our system, it may get transformed, it may get transferred, maybe at some point the air has most of it, maybe at some point the book has most of it. As long as all that energy stays in our system, we call this an isolated system. So the system is isolated if all the energy stays within the system. However, if energy starts to enter or exit, in other words, if something does work on our system, i.e. transfers energy in, or our system does work, transfers energy out by any means, then our system is no longer isolated because energy enters and energy exits. Again, don't get too hung up on the word work. Work is another word for the transfer of energy here, so you can just think about it pretty much as synonymous with transfer of energy. So if energy gets in or out, it's no longer isolated. And this might strike you as kind of arbitrary. We just picked our system to be all three objects. What's to stop us, you might ask? If you're clever, you might be like, what's to stop us from just, kicking the person out of the system? Now we can just say, what if we just said the book and the air? This is our system. Well, if we can do that, our system would no longer be isolated, and it wouldn't be isolated because energy is entering our system. So if the energy increases in our system, or if energy exits our system, if the energy can enter or exit, our system is no longer isolated. The same thing is happening. This person is still giving energy to the book, and the book gives energy to the air, and the air gives energy to the person. Nothing's changed about the physical situation, but the language we use to describe it will be different. We'll now say that our system of book and air is not isolated and energy enters that system. And we'll often use the word work to describe that transfer of energy. Before, when the person was part of our system, the work was done internally. All the energy stayed within our system. But now we have what we call external work. Now this person who's external to the system is doing work on the system, giving it energy. A simple way to think of all this is that if energy can leak out of your system, like it is right here, your system is not isolated. It's an open system. So the word we use sometimes to describe a system that is not isolated is open. Similarly, we could say closed is another word for an isolated system. But if energy can enter or exit your system, it's an open system. Now, if you're really clever, you might be like, hold on a minute. Wait just a minute. The thermal energy in this air, that can not just transfer into the person, that could transfer into the ground, that could transfer into the walls, that can transfer into the ceiling. There's going to be leaks all over the place. Doesn't that mean there's never an isolated system? Isn't there always going to be an energy leak? And the honest answer is pretty much yeah. It's really hard to make a truly isolated system. You can make insulated materials and try to isolate it with a vacuum, but even then it is extremely hard to make something that is completely isolated. We can get pretty close, and what we basically try to do in a lab situation or in a word problem is assume that all these little leaks here are going to be negligible compared to the big transfers of energy that we're going to keep track of. But in all honesty, yeah, hard to make a completely closed or isolated system. And so you might be like, all right, that's all well and good. That's a whole lot of good concepts, but how is this going to help me on the test? Think of the test, man. There's a test coming up. How is this going to help? And it helps because it makes explicit and helps us conceptualize the most important equation in all of energy and work. And that equation looks like this. It says that the initial energy of our system, whatever we're considering our system, whether it's book, person, and air, or just the book and the air, or even just the air, the energy of that system plus any external work that is done on that system. So if energy enters the system, this would be positive, and if energy exits the system, it would be negative because it's taking away energy from that initial energy. This has got to equal the final energy of the system. And this has got to be true because you can't just create energy or destroy energy. The only way to get energy is to transfer it from something else. There's a fixed amount of energy to go around here, and as long as no extra energy is entering or leaving the system, then the total amount of energy in that system is going to be fixed. However, if external work is done, if someone comes along and gives the system an extra 10 joules, then its final energy will be 10 joules greater than what it started with. And you might still be like, all right, that's still kind of abstract. I'm not going to be asked that kind of question. I might be asked, like, calculate this number. How do I find a number? I totally hear you. So check this out. You can make this a little more explicit by thinking about what are all the kinds of energies you can have. Well, one type of energy you can have is kinetic energy. So maybe there's some objects in your system that can have kinetic energy. You'd add up all those initial kinetic energies here. If there's things in your system that are moving initially, you put them in right there. If there's things that have gravitational potential energy, maybe things are lifted above the ground or above whatever point you're considering h equals 0, you'll have potential energies. You add all those up right there. Maybe you've got springs in your system. Maybe there's a spring there to worry about. You can add the spring energy, all that initial spring energy here. You could keep going. Maybe there's other energies. These are the three most popular that you meet in a physics context. So if you're taking a physics test, it's probably going to be one of these, most likely. And then add to that any external work that's done. Any work, right? If there's someone that came in and gave that system some extra work and they were not part of the system, you'd have to add that in here. And what's that going to equal? Well, it's just got to equal the final energy. So I'm kind of running out of room here. Let me move this. So if you add the external work to whatever energy you started with, that's got to equal your final energy. What form will your final energy take? It'll probably take the form of kinetic energy. There might be things moving. If there's things moving at the end of the process, whatever that was, your system's got some kinetic energy. Like maybe this book has a velocity and it has kinetic energy. You'll add to that whatever gravitational energies you end with. So if objects end up higher than they started, or at an h value that's above or below where you're considering h equals 0, then there'll be gravitational potential energy to end with. Similarly, if there's a spring and it gets compressed or stretched, you might have spring or elastic energy to end with. And then there's one more type of energy you could possibly end with. You might have generated some thermal energy. And so you can either write that as E thermal, or if you want to get explicit and solve for it, sometimes you can just leave it as E thermal, and maybe they just ask, how big is E thermal? Then you just solve for this quantity. This is the variable you solve for. Sometimes they want to know something more than that. Sometimes a test might want to know, how far did something slide before you generated enough thermal energy that it stopped? In that case, you'd want to figure out the magnitude of the work done by friction. And the work done by friction is just Fk, the force of friction, times the distance that object slides. This here is one of the most comprehensive equations that you could tackle problems with. This is a pretty general statement of conservation of energy. There are not many conservation of energy problems that you couldn't solve with this, and now you know what it means. You've got external work anytime energy enters or exits your system. It'll be positive if energy enters your system and negative if energy exits your system. Now, a lot of people don't like that. They're like, I don't want to deal with this external work at all. So what we can do is just say, that's fine. If you don't want this, then just call your system all of this. Make it encompass everything so that you don't have any leaks of energy, or if you do have leaks of energy, you can assume that they're negligible. That way, all the work that's done is done internally, and the energy of your system is conserved because no energy is exiting or entering your system.